Good morning, everybody. During the last lecture, we have discussed the work, energy, and the forces. But we have discussed the work for constant forces. Today, we will continue with work and energy with varying forces. So force will not be constant. And I will also give you some examples of non-constant forces. Here you see a particle, a box, let's say, on this surface. And this is the initial position of the box, x1. And we apply a force on this box to the right side. This is F1x. And here we have same box. Now we have the second position or final position. What do you see here? We have another force acting on this box. So this force is bigger than the initial force. So force is not constant. Okay? So what about the work done by this force on this box? From the last lecture, we remember that the work done by forces is given with this expression. Okay? This is the force, this is the displacement. Here from x1 to x2. But during the last lecture, we have considered that this force is constant. But now, the force is not constant. It is varying with time, with position. So here on the right side, we have a graph. This is the x-axis. This is origin. This is the force axis, okay? What do you see here? That this is the position 1, x1, and when the position is x1, the force applied on the box is F1x. And with changing position, the force is also changing. It is increasing, right? So finally, at position 2, we have much higher force compared to the position 1. So here we have a varying force. So what about the work done by these forces acting on this box? In order to calculate the total work done by this varying force, we divide this area into many small segments. Okay, this was the force versus position relation, and we divide this area into small segments, okay? And we consider that for very small displacements, we have more or less constant force. Here, for this displacement, we have more or less constant force. And in the third displacement, we have again more or less constant force. So we have small segments, okay? Then area of this column here, FAX times delta XA, and the area here in the second small segment, FBX times delta XB. So each segment gives us the work done by during this delta X displacement, okay? If you take some of them, if you integrate them, then you can calculate the total work done by this varying force on this box. So this is given with this expression. This is the work done by this varying force along the x-axis, and this is the lower limit of the integral initial position of the box here on the graph, okay? This is the x2 upper limit of the integral, final position of the box, and this is the integral of x component of force, okay? So we integrate force. Do you have any question here? This is the work done on a particle by a varying force. Just compare the work done by a constant force. Now here I have horizontal axis is the x position. This is the origin, and vertical axis is F here. okay? Fx force. This is the initial position of the particle. This is the final position of the particle, x2. What do you see here? That for each position of the particle, same F force acting on the box, acting on the particle, acting on the object. So the total area under this curve gives us work done on this object, F times S. This is F, this is S. What is S? Total displacement, x2 minus x1. So the area here under this curve gives us the work done on the particle. So just use this expression, work equation for varying force, and then put this constant force within this equation. Then let's see what will happen. Instead of Fx, I use this one here, this constant force, and then I integrate. So what is Fx? Fx here is constant. So you can take constant numbers out of integral, right? So now Fx is here. Then we have this integral. Integral from x1 to x2 dx. This is x2 minus x1, the solution of this integral. And here we have constant force. So what is x2 minus x1? This was displacement. So now we have the same result. So if you use this formula, this equation for constant forces, you can also get the meaningful results. Any question here? Now let me give you very nice, very important, and very widespread example of varying forces. Stretching a spring. Here we have a spring. It is at rest, let's say. It has certain equilibrium position. And then we are applying a force, which is given with k times x. Okay, we apply a force in this direction. And then we produce this displacement along the applied force. Here we have K. This is called as force constant or spring constant. Okay, the unit of this K is Newton per meter. Here, look at the equation of the force. This is given in Newton in terms of unit, and this is given in meter. Then the unit of force constant is Newton per meter. So let's compare the force constants of some materials. For example, a floppy toy spring such as Slinky has a force constant of about 1 Newton per meter. But for the much stiffer springs in an automobile's suspension system, K is about 10 to 5 Newton per meter. So this rule here, Fx is equal to K times x, is known as Hooke's law, okay? Here we have information. Real springs do not always obey on this equation here, which is given here, but it is still a useful idealized model. So we will discuss the Hooke's law more fully in chapter 11. So this equation comes from the Hooke's law. This is the applied force on this spring, and we have displacement of x. So what do you see here? Look at this equation. Let's consider that this position here is x is equal to 0. Then what about the force here? Force is given K times 0, then the force is 0. But here, when the position is x is equal to x, the force is given with this equation. So with increasing x, we increase the x, okay, F also increases. So what about the force? Force is not constant. It is changing with position, okay? Here we have a varying force. We have a non-constant force, and it is example for the non-constant forces or varying forces. So now we will discuss the work done by this varying force on spring. So now let's try to calculate the work done by this hand to stretch this spring. Here, let's consider you apply this force to the right side to stretch the spring. You apply the same force to the left side with opposite direction. But since left side of the spring does not move, since there is no displacement on the left side of the spring, then the work here done by this force is 0. But the work due to this force to the right side, we have displacement and we have certain work here. This is different from 0. So now we will calculate the work done by this force on spring. This work is given with this expression. Work is equal to 1/2 k times x squared. This x is total displacement, okay? From initial position to final position. Now let me show you here. This was the work formula for varying forces, which I have shown you in the previous transparencies, and then just put here fx dx. So let's consider that the initial position of the spring is 0. Let's consider that this is the x is equal to 0, and this is the final position of the x here. Okay, then instead of fx, just use here kx, the applied force. And k is constant, take this k out, and if you solve this integral, you will get this expression. Okay, actually it is like this. 1/2 kx squared minus 0. Okay, you will write this expression for upper limit and lower limit, and from the lower limit we will have 0, and from the upper limit we will have this one. So then the work done by hand on this spring is given with this expression 1/2 kx squared. So this hand does work on the spring, and spring does work on this hand, but the sign of the work done by the spring is negative. Why? Remember the last lecture. During the last lecture, we have seen 3 different conditions for the work. Look at the sign of the work done by hand on this spring. This is the direction of the force. This is the direction of the displacement. Since the displacement and force are in the same direction, the work is positive. What about the work done by spring? Here we have an opposite force with the same magnitude, and the direction is along negative x, let's say. Here we have displacement of the spring. It is in positive direction. Since the force and displacement have different directions opposite to each other, then the spring does negative work. Okay, don't forget this one. So we have taken this equation from this formula, work for varying forces, but you can also get this result from this graph. Look at the graph here. This is the position x, okay? This is the origin, initial position. This is the final position x, and this is the force. So what about the force? Force is given with k times x. So if you increase the x, then F is increasing. So we have this type of relation for the force. And the area under this curve will give us this relation. Okay, if you multiply 1/2 kx and x here, then you will get this result. Okay, just from the geometry, you can get this area here. This is the work done by this varying force. Any question here? Let me show you here the difference between stretching and compressing. Let's consider that this is the equilibrium condition here. X is equal to 0. And this is the stretching, okay? Displacement in this direction. And this is another condition. Here I have displacement in this direction, okay? This is compressing. This is stretching, okay? The difference in between. Any other question? Okay, let me continue with another condition. Let's consider that at the beginning, the spring is stretched a little bit, and the initial position of the spring is here. X is equal to x1. And now, from this position to another position, I would like to further stretch the spring, okay? I would like to elongate it. So now, what about the work done on the spring? The work done on spring to stretch this spring from position 1 to position 2 is given with this expression, x1 to x2. Instead of fx, just put kx, and then you will have this integral. K will go out, and if you solve this integral, you will have 1/2 kx2 square minus 1/2 kx1 square. So if the initial position is 0, then you will put here 0, then you will get this result. So you will have the same result here in the previous transparency. But if the initial position of the spring is different from 0, then you will have this expression. So here we have the graph of this type of condition. This is the position of the spring, this is the applied force, and this is the equilibrium condition for the spring, but this is the initial position for the spring, x1. And at x1, we apply kx1 force, and at x2, we apply kx2 force, and this is the area which will give us the work done by this force on this spring. So you can also calculate the area of this, then you will get this expression. Okay, by using geometry, you can get the same relation also. Here we have caution from the book, work done on a spring versus work done by a spring. I have already discussed, but here I will read the caution. This equation here gives the work that you must do on a spring to change its length. So in order to change the length of the spring, I apply this force and I do this work on spring. If you stretch a spring that's originally relaxed, then x1 is 0. What is the meaning of this one? Originally, the spring is relaxed, and then you changed its position to x2. Okay, then you done a work on the spring. The force you apply to one end of the spring is in the same direction as the displacement, and then the work you do is positive. I have already told you. By contrast, the work that the spring does on whatever it is attached to is given by the negative of this one. I have already discussed this one because the direction of the force applied by spring and also direction of the displacement are opposite. Thus, as you pull on the spring does negative work on you. I have already explained this one, but it is just to remind you. Okay, now let me continue with this example from the book 6.6, work done on a spring scale. Here there is a bathroom scale, okay, and there is a woman on this weighing scale. So a woman weighing 600 Newton steps on a bathroom scale that contains a stiff spring In equilibrium, the spring is compressed 1 centimeter under her weight. So woman is here and then applies a force, weight of this woman, and then she compressed the spring with this 1 centimeter, okay? Look at the term, compress, okay? Not stretch, because we decrease the length of the spring. This is compression. Find the force constant of the spring and the total work done on it during the compression. So let's choose, this is the positive x direction, upward, and downward, let's choose negative x direction. Actually, you can also choose positive y here and negative y here, okay? Or you can choose vice versa. So instead of fx, kx, you can also write this formula, okay? This one. But this is not necessary here. If you choose positive x is upward and negative x is downward, then you compress the spring with this magnitude, -1 centimeter, okay? And it is equal to -0.01 meter. And woman exerts force, which is given in the question, 600 Newton. But what about the direction of the force? The direction of the force applied by the woman in negative x direction, okay? Then you can write it like this, -600 Newton. Then what about the force constant of the spring? We have this formula, K times X. And if you take force constant from this equation, then you can get this relation. Here we have -600 Newton over -0.01 meter. Then we have this force constant for this stiff spring. And what about the second question, the total work done on it during the compression? So this is the work formula, 1/2 kx2 square minus 1/2 kx1 square. So what was the initial position? Initial position is 0 because at the beginning it is at rest, okay? It is in equilibrium and the spring is relaxed at the beginning. So then this term will be 0, okay? And work done by woman on this spring is given with this expression, 1/2. This is the force constant of the spring. And here we have the displacement, final position, minus 0.01 meters square. So if you take the square of this one, this minus sign here will be positive, and the result is 3 joule. Actually, look at this one. This is the direction of the force, and this is the direction of the displacement. So since the displacement and the force applied by the woman are in the same direction, then of course the work will be positive. Any question? Here, where is it? So this spring does a negative work on this woman, okay, with the same amount but opposite direction. So the force applied by spring on the woman is given with this positive Fx, and the compression is along the negative x direction. Then this spring does a negative work on the woman. Any question? Then let me continue with work energy theorem for varying forces. During the last lecture, we have seen work energy theorem for constant forces, and we got this relation. This was the total work done on particle by net force, which was equal to final kinetic energy of the particle minus initial kinetic energy of the particle, and it is equal to the change in the kinetic energy, delta K. So we have written this equation for constant forces. So what about the varying forces? So this equation is still valid or not? Now let me do some calculations. Here we have a spring, and at the beginning the position is x is 0, initial position. The spring is relaxed, and then I apply a force to the right side, which is given with Fx times Kx. So what do you see here? This force is a varying force. Depending on the position of the spring, the force changes, okay? So what about the acceleration of this part of the spring? So since we have force, net force, then we have an acceleration. Remember the Newton's second law, right? So what about the x acceleration of this spring? It can be written with time derivative of its x velocity, okay? dvx over dt. So if I multiply this term with dx and divide by dx, so I multiply this term with dx and divide with dx, nothing will change, okay? So then here I have the x derivative of vx, and here we have dx over dt, time derivative of x. This time derivative of x will give us the velocity vx, right? dx over dt will give us vx velocity, and here we have dvx over dx. So then here we have acceleration. Now I have a term for the acceleration. Now let's try to calculate the v total, the integral from initial position to final position, f times dx. Here we have fx. Instead of fx, I use this one. Net force is equal to m times ax, right? So instead of fx, I use m times ax. Then instead of ax here, just use this expression. Put this one into the integral. Here we have m, here we have vx, here we have dvx over dx, dx. So this one will cancel this one, and this m is constant. It will go out of integral, okay? So here we have this integral, m vx dvx. So what about the solution of this integral? You can also write this one like this. v1, v2, vx, dvx. So what do you see here? The integral limits were at the beginning x1, x2. Now we have integral limits v1, v2. Initial velocity of the spring and final velocity of the spring. So if you solve this integral, you will get this expression, 1/2 mv2 square minus 1/2 mv1 square. So this is the final kinetic energy of the particle. This is the initial kinetic energy of the particle, and it is equal to delta K. So this is the V total. What do you see here? This is equal to the work energy theorem for constant forces. So it means that this theorem, work energy theorem, valid for constant forces and varying forces. Don't forget this one. Any question here? Now let me show you a bio application. Tendons are non-ideal springs, so we will consider that tendons like springs, okay, but non-ideal springs. Muscles exert forces via the tendons. We have discussed this one during the last lecture. Muscles exert forces on tendons, okay? And the tendons that attach them to bones. A tendon consists of long, stiff, elastic collagen fibers. These tendons are long, stiff, and elastic collagen fibers. So here we have a graph. What is the graph? Extension of the fibers, extension of the tendons, okay? So this is the, let's say, initial length of the fiber, and then muscles exert forces on these tendons, and the length of the tendon increases, okay? So this is the extension, and this is the force exerted by tendon, okay? So the graph shows how the tendon from the hind leg of a wallaby stretches in response to an applied force. The tendon does not exhibit the simple straight line behavior of an ideal spring, so the work it does has to be found by integration. So what you see here, this is the extension, let's say X position, okay? And this is the force, so force is not constant, okay? So the work it does has to be found by integration. The tendon exerts less force while relaxing than while stretching. Look at this one. This is the stretching of the tendon. You elongate the tendon, you increase the length of the tendon. So then the force exerted by the tendon is given with this expression. This is the maximum tendon extension, maximum stretching you can consider, and then the tendon relaxing back to its initial condition, okay? So we have different forces during the stretching and relaxing, okay? Which is given here. As a result, the relaxing tendon does only about 93 of the work that has done to stretch it. So during the relaxing, it requires less work. Any question here? This is bio-application of the springs, varying forces, let's say, and work done by varying forces. Okay, this is example 6.7 from the book, motion with a varying force. There is an air track glider of a mass, which I have explained before the midterm exam. This is the air track glider. You apply air from this side and you produce more or less frictionless surface between the glider and this surface. And here we have a spring, okay, with some certain force constant or spring constant. This is the mass of the glider, and this is the velocity of the glider. An air track glider of mass 0.1 kilogram is attached to the end of a horizontal air track by a spring with force constant 20 Newton per meter. Initially, the spring is unstretched and the glider is moving at, look at the information here. Initially, the spring is unstretched. Then you can consider that it is at 0 position. X is equal to 0, unstretched. But the glider is moving at 1.5 meter per second to the right. The glider is moving to the right, okay? It has certain velocity. Question, find the maximum distance d that the glider moves to the right if the air track is turned on so that there is no friction, and if the air is turned off so there is friction, kinetic friction with coefficient mu k is equal to 0.47. So, two conditions. At the beginning, this air track stays here, but it has certain velocity. How it could be possible? Let's consider that it was compressed at the beginning, and after it is released, it is moving to the right side, and at this position, which is x is equal to 0, it is passing with some certain velocity, and then it will reach to the final position here. This is the maximum distance, is given with d, okay, in the question, maximum distance d. So this is asked, but this maximum distance is asked for two conditions. In A, there is no friction, so the air track is active and there is no friction between the glider and the air track, okay? And in the second case, the air is turned off, so there's a kinetic friction between the surface of this one and the glider here. Okay, now let's try to write the free body diagram for two conditions. If there is no friction, we have this type of free body diagram. Let's choose that this is the positive y direction, this is the positive x direction. Here we have weight of the glider. Here we have normal force applied by the air track, and this is the F spring. So what do you see here? This mass, this glider is attached to the spring and it is going in this direction. So the position changes from 0 to certain distance. For this reason, spring applies a back force. So this glider applies a force on the spring and then spring applies a back force. This is the weight of the glider, which is given with m times g because mass is given. And this surface, this air track, applies a back force, which is normal force, okay, in positive y direction. And we have a spring force. So since this mass, this glider, moves in this direction, this glider applies a force to the right side on the spring. Then the spring applies a back force with opposite direction. So this is the force applied by the spring on the glider. Is the free body diagram clear? If the free body diagram is not correct, then it is not necessary to continue. If you don't understand the free body diagram, it is not necessary to continue. Free body diagram is very important, always when you are solving, dealing the questions. Now let's discuss the second condition. If the air is turned off, and then if there is a friction between the glider and air track, then what will happen? We have weight again in downward direction. We have normal force. We have F spring to the left side, but we have a friction force to the left side due to the friction between glider and air track. Why the friction is to the left side? Because movement of the glider is to the right side. Friction force is always opposite to the movement, don't forget. So now we have two free body diagrams for two different conditions with friction and without friction. What was the question? What is the maximum distance that the glider moves to the right if there is no friction, if there is a friction, kinetic friction? Here we have the solution. First of all, let's calculate the work done by the glider on spring. The work done by glider on spring can be written with this expression, 1/2 kx final square. So what is the final position? Final position is D, which is given in the question. What was the initial condition? Initial condition is given. Initially, the spring is unstretched. Unstretched means, uncompressed means, this object is staying at x is equal to 0, okay? It is not stretched, it is not compressed. So this is the initial condition. So work is given with 1/2 k d square minus 1/2 k the square of initial position. It is 0. Then the work done by the glider on the spring can be written with this form, 1/2 k d square, okay? And the amount of work that the spring does on the glider is the negative of this one. So this spring will also do work on this glider because this spring applies force in this negative x direction, displacement to the positive direction, then the spring will do negative work on the glider. Then what about the kinetic energy? So at the beginning, the kinetic energy of the glider is given with this velocity. Finally, when the maximum distance d is reached, what is the velocity of glider? Glider stops there. The final velocity of the glider is 0. Then the final kinetic energy of the glider at the position d, at distance d, will be 0. So then initial kinetic energy is 1/2 mv square. Final kinetic energy K2 is 0. So just write work energy theorem. So this is the work done by the spring minus 1/2 kd square, which is equal to final kinetic energy. Final kinetic energy is 0 minus 1/2 mv square, initial kinetic energy. So from this relation, you can get the d. D can be written with V1 square root of mass of the glider over force constant of the spring. Then put all numbers into this equation. Then you can get the d is 0.106 meter or 10.6 centimeter. So here, this is the first condition. And what about the second condition? If the air is turned off, we must include the work done by the kinetic friction force. Okay, so kinetic friction will also do work on the glider. And the work done by the kinetic friction will also be negative because displacement to the right side and the applied kinetic friction force to the left side, then there will be negative work. What about the kinetic friction force, which is given with mu k times n? We have learned this one in chapter 5. Instead of n, just write m times g, okay, because n here is equal to m times g if you apply Newton's first rule. Then the work done by kinetic friction is given with this expression fkd cosine 180 degrees. The angle between the displacement and the kinetic friction force, this angle is 180 degrees because this is the direction of the displacement, this is the direction of the kinetic friction, and the angle is 180 degrees. They are opposite to each other. For this reason, the work done by the kinetic friction is negative fkd. Instead of fk, just use mu k mg. Then here we have kinetic friction. So the total work is the sum of the work done by kinetic friction and the work done by the spring. So look at this one. When we have a friction, we have two forces to the left side. One is F spring, the other one is kinetic friction force. And we have displacement to the right side. So both F spring and Fk do a negative work on this glider. So the total work is given with the work done by the kinetic friction force and the work done by spring. So both of them have negative signs. So what about the change in the kinetic energy of the glider? Final kinetic energy minus initial kinetic energy. Final kinetic energy is 0 because after certain d distance, the glider stops. So it has no kinetic energy here at the maximum distance. Okay, then from this equation, you can get the if you put all numbers into the equation, you will get this expression, 0.086 meter. So look at this one. This is 8.6 centimeter. If you convert this one from meter to the centimeter, 8.6 centimeter. If there's a friction, this is the maximum distance. But what about the maximum distance if there is no friction? If there is no friction, we have 2 centimeter more distance compared to the distance with friction. Any question here? Okay, let me continue with work energy theorem for motion along a curve. So during the first lecture on Tuesday and during the first part of this lecture, we have discussed the work energy theorem for a motion along a straight line. But what about the work energy theorem for motion along a curve, like a curve path here? Here we have a particle, and this is the initial position of the particle P1, and this particle is moving along this curved path, okay, from P1 to P2. And this type of force with this direction and magnitude applies on this particle. So what about the work done on this particle? So remember the formula for the work which we have done during the last lecture. The general formula for the work is given with F times displacement, or Fs cosine phi, the angle between F and S, okay? Or we can also write this one, F parallel times S. So this F cosine phi can be written as F parallel. Okay, we have discussed all these things during the last lecture. So this particle is moving along this path from position 1 to position 2. And at this point, I would like to write the work done on this particle. So here we have a force like this in this direction. Okay, this is the angle between the displacement and force. So what is dl here? Instead of S, here I use very small segment of the path, okay? I consider that this is more or less linear, okay? An infinitesimal displacement dl instead of S. So then, instead of S within this equation, I just use dl, F cosine phi dl, during an infinitesimal displacement dl. This work, F, does work dv on the particle. Okay, let's say an infinitesimal work on this particle during an infinitesimal displacement. So what about the total work acting on this object, this particle along this curved path? For this one, I have to apply a line integral here. So integral from P1, lower limit, initial position, to the P2, upper limit, final position, F times dl. This is scalar product, okay? Since this expression is scalar product, I can write it like this, F dl cosine phi, or F cosine phi dl. So what is this F cosine phi? F cosine phi is F parallel, component of this force parallel to the displacement, okay? So then we have work done on a particle by a varying force along a curved path, this expression. Any question here? Then let me continue. What about other components? Here we have two components of force. One is along the displacement, and the other one is perpendicular to the displacement. So we know that only the component of the net force parallel to the path, this is the displacement, infinitesimal displacement, and this is the parallel component of the force. And this force does work on the particle. So what is the result? Due to the work done by this force, the speed and kinetic energy of the particle can be changed, okay? What about this perpendicular component of the force? Since the cosine phi is 0, because this is 90 degrees, cosine phi is 0, there will be no work done by this perpendicular component of the force. But what about the duty of this perpendicular component? Remember the uniform circular motion, non-uniform circular motion. So this perpendicular component helps us to change the particle's direction, okay? This component only changes direction, but the speed and kinetic energy of the particle is changed by this parallel component. So then we have work done by a varying force acting on a particle along a curved path. Here, let me give you another example from the book related to this part of my lecture, motion on a curved path. At a family picnic, you are appointed to push your cousin in a swing. The name of cousin is Throckmorton. His weight is W. The length of the chains is R. So this is the swing, okay? This is the chain. And weight of the cousin is W, which is given. R is the length of the chain, okay? Chain of the swing. And you push Trocky until the chains make an angle theta 0 with the vertical. This is the vertical axis, and you apply push force on this guy to this side until this theta becomes theta 0. Where is it? Here, okay? To do this, you exert a varying horizontal force that starts at 0. So you apply force in this direction until certain theta degrees, let's say, but at the beginning, the force is 0, okay? And you have to increase the force, so you apply a varying force. Okay, it is clear, but another important information here is that the swing moves very slowly and remain very nearly in equilibrium throughout the process. If the system is very nearly in equilibrium throughout the process, you can consider that the net force acting on this guy is 0, okay, throughout the process. So now let's see the questions. What is the total work done on trockees by all forces? What is the work done by the tension in the chains? So here there is a chain and there's a tension force applied by this chain on this guy. What is the work done by tension T in the chains? What is the work you do by exerting force F? So you apply force in this direction to the right side. So what is the magnitude of the work and what is the sign of the work you do on this guy? What about the free body diagram? The free body diagram of Throckmorton, this guy, is given with this expression. We neglect the weight of the chains and we neglect the weight of the seat here. Just consider weight of the guy in this direction, downward direction, let's say negative y direction. And there is a tension force applied by the chain on this guy, okay? And this tension force has two components. One is perpendicular component, which is given by T times cosine theta. Here we have theta. With this relation, you can write this one. And this is the horizontal component of the tension force, T times sinus theta. So What about other forces? There is another force you apply, push force to the right side, acting on this guy. Okay, now we have free body diagram, three forces: push force, weight, tension force. And here we have components of tension force. So now, first question: what is the total work done on trachea, this guy, by all forces? Here, in the question, it is given that the trachea is nearly in equilibrium at every point. What is the meaning of equilibrium? The net force on him is zero in equilibrium. The integral of the net force is zero. Then the total work done on him is zero. Okay? If the net force is zero, work is zero. So then the total force acting on this guy is zero at any point during this process. So, second question: what is the work done by the tension force? How to calculate tension force? So what do you see here? Look at the picture, please. Let me draw in order to understand this question. This is the direction of the tension force applied on the guy, okay? And this is the displacement, you see, dl. For any time, this displacement and tension force are perpendicular to each other. So work done by tension force, T times dl, or T dl cosine theta or cosine phi, let's say, since they are always perpendicular to each other along this circular path. Let's consider that this is part of circular path, and cosine 90 will be zero, so work done by the tension force will be zero. Okay, this was the answer of the second question here. And the last one: what is the work you do by exerting force F? So what is the work done by this F? How to calculate this one? We can use the free body diagram here. So calculate the net force along the x-axis, calculate the net force along the y-axis. So what about the net force along the x-axis? We have F applied by U, which is positive because it is along the positive x. And here we have T sinus theta. It is along the negative x, so it has negative sign. And what about the net force? Since the system is nearly equilibrium at all points, net force is zero. Okay, then we have this relation. You can take this expression from this equation, T sinus theta. Now we have relation between tension force and push force applied by U. So what about the net force along the y-axis? We have this one, positive, and we have weight in negative direction. Then they are also equal to each other because system is nearly in equilibrium at all points. Then I can write this one. Weight is equal to T times cosine theta. Okay, here we have T. If I take T from this expression and put it there, then I can get this expression. F is equal to W times tangent theta. Let me write. So look at this term. T is equal to weight over cosine theta. So use this T here. Okay, then this force will be like this. F is equal to, instead of T, weight over cosine theta. Here we have sinus theta. Sinus theta over cosine theta will give you tangent theta. So force is given with W times tangent theta. Okay, now we have found the force applied by yourself in terms of weight and theta angle. Let me clean this part, then I will continue. What is the magnitude of work done by this F force? What about displacement? So here we have the work done by F force. You apply force in this direction, and then this is the displacement along a curved path. So since we have a curved path, we will use line integral. Okay, here we have P1 from integral from P1, position 1, initial position is this one, to the final position P2, F cosine phi dl. This is the equation here which we have produced. Okay, then what about F? F is calculated here. Just use this F here instead of F. And what about dl? What is dl? Displacement. Okay, in the S, the arc length S. So just consider that. Here you have a circle, and here you have S. This S is given with this expression here. I mean displacement along a curved path, let's say, okay? S is R times theta. So we are talking about dl, infinitesimal displacement. I can write it like ds. So ds is R times theta. During this displacement, only theta changes, R is constant, okay? So then dl can be written with this expression, R times d theta. So instead of dl here, just use this expression. Instead of f, just use this expression. Here now I have omega times tangent theta, cosine theta. What is cosine theta? The angle between f and dl. Instead of cosine phi here, I use cosine theta because theta is given in the question. Instead of dl, I use r d theta. So then finally, this is the force, okay? Sorry, this is the work done by this force. What we have here, the limits from 0 angle to final angle theta 0 here, which is given in the question, okay? Weight of the guy, radius of the circle or length of the chain times sinus theta d theta, okay? So this is the integral, and if you know the weight, if you know the r, if you solve this integral, and if you know the final angle, then you can get the work done by this push force on this guy. Any question? If you solve this integral, you will get this expression. Let me also discuss this one. So this was the final integral, okay? Work done by the force. So weight is constant, r is constant, take them out of integral. Now here we have integral from 0 to theta 0, sinus theta d theta. The integral of sinus theta is minus cosine theta, limits from 0 to theta 0, okay? Then cosine theta 0, and what is cosine 0? Cosine 0 is 1, then here we have minus 1. So if you multiply this one with minus sign here, then finally work done by this force can be written in this form. Any question? Now let me finish my lecture with power. This is the last part of my lecture. What is power? We have learned work. We have learned the relation between force and work. We have learned the relation between kinetic energy and work. So what is power? And what is the difference between power and force? Power tells us how quickly work is done. We have two equations. The first one is for average power during the time interval dt. Average power is given with work done during time interval over duration of time interval delta t, like other definitions of average velocity, average acceleration, average displacement, something like this. And here we have instantaneous power. Instantaneous power is given with limit delta t goes to 0 for a very short time, very short moment. Okay, we have delta v. So you can also write this one, time derivative of the work. This is the time rate of doing work. And we have average power and instantaneous power. So what is the unit of this power? What was the unit of the work? Unit of the work is joule. Okay, unit of the time is second. Then the unit of power is joule per second or watt. Okay, 1 watt is equal to 1 joule per second. And another unit of this power is horsepower, in Turkish beygir gücü. 1 horsepower is equal to 746 watt. For example, the power of the car is given with horsepower in conventional cars, but in electricity cars, usually this watt is used to express the power of the cars, okay, kilowatt or megawatt, okay. So in order to express the power of the objects, for example, power stations, then we have two common units for the power. One is watt, which is equal to 1 joule per second. The other one is horsepower. Then let me explain a little bit what is the meaning of how quickly work is done. Here we have a box. Okay, when the time is 0, box is staying here, and we lift this box to this position in 5 seconds. And you do work to lift this box. What about your power? Your power is work per time. And work is 100 joule, time is 5 seconds, and your power is 20 watt. Okay, but this is the initial position of the box when the time is 0. Now this is the final position. Let's consider that the distance between initial position and final position is same for both cases. Here in the first case, same displacement is taken within 5 seconds, and in the second case, displacement is taken within 1 second. Okay, you do the same work, but what about the power here in the second case? In the second case, work is again 1 joule, okay, and time is 1 second. Now your power is 100 watt. Here 20 watt, here 100 watt, okay. The power is higher here because you can lift this box within a shorter time. So power shows us how quickly work is done. Let me discuss the relation between power and velocity. Okay, here we have defined the power with work and time, and now I will define the power in terms of force and velocity. Let me draw. Here we have a box, let's say, and this force acts on this box, and this box has this displacement. This is the displacement delta S along the same direction. But sometimes force can be like this. Then you have to consider parallel component of the force. Okay, so suppose that a force acts on a body while it undergoes a vector displacement delta S. Okay, then the work done by this force is given with delta W, which is equal to parallel component of the force and the displacement. What about the average power. Average power is given with this expression. And here we have calculated delta V, put this delta V in average power, and we have F parallel times delta S. What do you see here? Delta S over delta T. What is delta S over delta T? This one. This is the V average, right? Average velocity. This is the average power in terms of average velocity. If delta T goes to 0, I mean for very short time, this V average goes to instantaneous velocity, and this P average goes to instantaneous power. Then instantaneous power can be written in this form: parallel force acting on the object and the velocity of the object. Since this is a scalar number, power is a scalar, but the velocity is vector, force is a vector, I can write this one as a scalar product, okay? F times V, force acts on a particle, this F, and V, velocity of particle, and this is the instantaneous power for a force doing work on a particle. This is the relation between power and force and velocity. Here we have power is given with work over time interval, okay? And here we have power F times V in terms of force and velocity. And sometimes this is very useful. Sometimes this is very useful. Depends on the question, depends on the application. So instantaneous power and average power have two different types of definition. Any question here? Let me continue with the bio application and muscle power. Here you see a part of a fish. Skeletal muscles provide the power that makes animals move. Muscle fibers that rely on anaerobic metabolism do not require oxygen. They produce large amounts of power, but are useful for short sprints only. Muscle fibers that metabolize aerobically use oxygen and produce smaller amounts of power for long intervals. Both fiber types are visible in a fish fillet. Here you see a fish fillet. So the pale anaerobic muscle is used for brief bursts of speed, while the darker aerobic muscle is used for sustained swimming. Okay, this colored one, these darker ones are aerobic muscles, okay, and they are used for sustained swimming for a long time. And for, let's say, pale ones here, anaerobic muscles are used for brief bursts of speed. Any question here? This is the application of power in muscles. Of course, in human body, we have also this type of muscles, and also in other animals, there are many types of muscles, and with this property of the muscles, we can, and animals can produce power. Okay, now let me finish this lecture with two examples. This is the example 6.9 from the book, Force and Power. What is the relation between force and power? Here you see an Airbus A380 airliner with 4 engines. You see 4 jet engines. And here we have very old one compared to this one. This uses also, how to say, 1, 2, 3, 4 engines, I think. Each of the 4 jet engines on an Airbus A380 airliner develops a thrust, a forward force on the airliner, a thrust of 322,000 Newton. When the airplane is flying at 900 kilometers per hour. This is the common speed of the planes, okay? For example, distance between Istanbul and Düsseldorf in Germany is around, let's say, 3,000 kilometers. And with this speed, roughly within 3 hours or within 3.5 hours, you can reach from Istanbul to Düsseldorf, okay? So the question, what horsepower does each engine develop within this Airbus airliner? Here, what is the information? Each of the 4 jet engines develops a thrust of 322,000 Newton. Okay, this is not the total thrust. This is the thrust produced by each jet engine. Okay, and here the question is, what horsepower does each engine develop? So what about the solution? Velocity is given. Velocity is 250 meters per second. Okay, or 900 kilometers per hour. So force of each engine is given. This one, 322,000 Newton. Put it there. Put the velocity here. Then you can calculate the power in watt. Okay, and you can convert this watt to the horsepower. Then here we have 108,000 horsepower from each engine. In total, more than 400,000 horsepower. Now let's compare with the older ones. The largest propeller-driven airliners of 1950s had engines that each developed about 3,400 horsepower, 10 to 6 watt. Look at the horsepower here from each engine of the modern airliner. 108,000 horsepower, and each propeller here in older airliners provides 3,400 horsepower. This is the huge one in the modern airliners, giving them maximum speed of about 600 kilometers per hour. So the maximum speed of this airliner is around 900 kilometers per hour, and the older airliners have this type of speed. If the engines are at maximum thrust while the airliner is at rest, so let's consider that this airliner is at the airport on the ground, okay, and its speed is 0, but the engines are producing maximum thrust. So engines are working, but the velocity is 0. It is staying on the ground. The engines develop 0 power because velocity is 0. Okay, if here you have huge force produced by each engine of jet motors here, but velocity of the airliner is 0, then the power will be 0. Force and power are not the same thing. You have force on the engines when the airliner on the ground, but since there is no velocity, there is no power. This is a special condition if the airliner is staying on the ground at rest. Any question here related to this example? Okay, this is the example 6.10, a power climb. Here, there is a runner. She climbs this very tall building, okay? A 50-kilogram marathon runner runs up the stairs to top of Chicago's 443-meter tall Willis Tower. The length of this building is 443 meters, and this is the second tallest building in the United States. To lift herself to the top of this building in 15 minutes, what must be her average power output? So she runs on this stairs and starts from this position and goes to the top of this building in 15 minutes. Okay, so what about the average power output? Express your answer in watts, in kilowatts, and in horsepower. What about the free body diagram of this lady? Here, there is a weight in downward direction, and these stairs apply normal force to this lady. And only normal force is acting on this lady, this runner, okay? So due to this upward force applied by the surface of the stairs, this lady has this type of movements in upward direction. So what about the work done by this normal force applied in upward direction? The work is given with n times h, distance, displacement, okay? This is the normal force mg times displacement, height of the building. So m is given, g is we know, and what about the length of the building, which is also given? Put them here. Then the work is 2.17 times 10 to 5 joule, okay? So the question, average power output, average power is given with delta W and delta T. Delta T is 15 minutes or 900 seconds, put here second. And delta W, the change in the work, is given with this expression, put them here. Finally, we have 241 watts or 0.241 kilowatts or 0.323 horsepower. So what do you see? Average power of this runner is more or less 3 times smaller than single horsepower. Okay, this was one solution. This is the solution one. Then we have found the result in watt, kilowatt, and also horsepower. This is the solution. But I can also solve this question by using another expression of the average power. Remember this formula. Average power is also related with force and velocity with this expression. So average force is normal force in upward direction. And then velocity, what is average velocity? Is it given? Average velocity, you can calculate average velocity. You know the height of the building and you know the time. So displacement over time, right? Displacement over time. Then you can get the velocity of this lady, put the average velocity here, and then you can calculate 241 watt, okay? They are same. So by using average power formula, which is given delta W over delta T, or average power formula, F parallel times V average, you can calculate the power. Any question? If not, I will finish the lecture. Please try to solve all questions and problems at the end of the chapter. Then you will understand the topic better and you will get very good results in quiz, and also you will get very good results in the second midterm exam. So take care of yourself. Bye-bye.